In this video, we're going to talk about arc length. So usually when we think about lengths of things, we're thinking about lengths of straight lines or line segments. But for a general rule, we would like to be able to have a formula that comes up with the length of a curved segment, if you will. Now, generally speaking, we don't have many formulas for doing that. Really, the only one that we know up until this point is finding the circumference of a circle. Everything else that you think about what you know formulas for figuring out lengths, they're all line segment ideas, except for circumference of a circle. So we want to try to extend that notion here. So we want to try to find the length of a graph of a function, call it y equals f of x for the time being, where x goes from a to b. All right, so let's say we have this function, just some arbitrary function here, and I want to know what the length of this piece of that function is. And certainly this is rounded, right? This is not line segments at all. Okay. However, just like we've done everything else up until this point, we will use a simpler geometric idea to approximate the quantity that we're looking for. We will then add up those approximations and recognize that we have a Riemann sum. So that's the idea here. We're going to do the same thing as we've done in the past with other concepts. So we're going to partition our interval a to b into n subintervals of equal width. And what we're going to do is we're going to consider the line segments that have endpoints x sub I minus 1, f of x sub I minus 1, and x sub I, f of x sub I, going from 1 to n. So remember again, when you do your partition, the a is your x naught, your b is your xn, and so we'll have points in between. So we think about the picture here. I don't have very many points in here because I wanted to illustrate what's going on with the line segments. So here, at this point here, this would be your x1 on your x-axis, so your y-coordinate corresponding to that would be f of x1. So your first segment would go from x naught, f of x naught to x1, f of x1. The next one would go x1, f of x1 to x2, f of x2, and continuing on with all of these sticks. Okay, so these line segments, these sticks ideas, these are the things that we're going to figure out the lengths of. And again, we already know how to do formulas for line segments, or we know a formula for lengths of line segments. So let's just concentrate on one such line segment and then add them together at the end. This is just our usual distance formula between 2 points, right? This is x2 minus x1 plus y squared plus y2 minus y1 squared. This is just our usual distance formula. We're just using our x coordinates and our y coordinates as we wrote them in terms of the endpoints in the previous slide. This doesn't look like anything that has to do with a Riemann sum piece, right? This doesn't look like the form function times delta x. However, I do see hidden in here a delta x piece. So let's see if we can get that sticking on the outside. So the first thing we're going to do is we're going to factor off this x sub I minus x sub I minus 1 squared off of these two terms. Now, of course, we don't see it in the second term, so I'll have to divide by it. So when I factor off the x sub I minus x sub I minus 1 squared, I'll have that x sub I minus x sub I minus 1 squared in the denominator. And I just pulled out the square over top and bottom. So I've got 1 plus this fraction squared. Now I've got a product on the inside of my square root, so I can just take the square root of that first piece, pull it out, and I'm just going to put it at the end. And then I notice that I don't need to worry about absolute value here, by the way, because x sub I should be bigger than x sub I minus 1, right? We're going from left to right across with our indices here. So I don't need to worry about absolute value, but what I do recognize is that this is the length of the ith subinterval, and that's what we denote with delta x. So at least I've got part of what I need. I see something times delta x, but it's not just function of a sample point times delta x. So I need to play with what's inside here and see if I can see function of sample point instead of this functions of two sample points or 2 points, and really aren't sample points here. They're endpoints in our partition. Now let's concentrate on this fraction, however. This is change in y, essentially, right? Difference in your function values. So this is change in y over change in x. When you have change in y over change in x, that should make you think slope. And one of our first interpretations of slope for functions generally was the derivative, right? So this should make us think of derivatives. So let's see if we can get the derivative involved. Well, in order to be able to get the derivative involved for a particular function, I better make sure that the function actually has a derivative everywhere that I'm interested in. So to make things simpler to start with, we're going to assume that our function is what's referred to as smooth, and I'll get this definition on the next slide. This part here is just saying that when we've got these approximations for our lengths, we're just going to add them up to get our approximation of our arc length. But this isn't quite a Riemann sum like we mentioned, right? Because this is not function of a sample point times delta x. All right, so, but we did say that that reminds us of derivative. Derivative, we need to make sure we can take the derivative all the time. So we're going to assume that we have what's referred to as a smooth curve. Smooth just means that you can take the derivative of the function and the derivative is continuous. So we don't have any jumps in our derivative. So basically we're making sure that we don't have any sharp corners, we don't have any cusps, any of those kind of things. It's just a nice, smoothly drawn out curve. Okay? All right, so if it's smooth, that means that our derivative, again, is continuous on the entire interval from a to b, which means that we can apply the mean value theorem to the original function. Remember, the mean value theorem applies to a function that is continuous and differentiable. Well, if it's continuous, if the derivative is continuous everywhere, it certainly means the derivative is defined everywhere on that interval. All right. And if it's defined everywhere on the interval, it's certainly defined everywhere on the subinterval. So we can apply the mean value theorem to each subinterval. We can find a sample point so that the derivative at that sample point is equal to that slope expression that we saw on the previous slide. So now we're going to take each of those slope expressions, replace it with the value that we're guaranteed with by the mean value theorem. Now we have sum of function times delta x. This is now a Riemann sum. So when we take n goes to infinity, we have this expression for our arc length. Now notice that in this case we were given y equals f of x to start with. You could go back and have a function of y, having x equals a function of y to start with, and this all would be exactly the same idea. So this formula will work even if you have a function of y rather than a function of x. Of course, you just need to make sure that your limits of integration are in terms of y rather than x. Let's see if we can do an example. All right, so to make our lives simpler, let's just say we have the function y equals 2/3 x to the 3/2 on the interval from 8 to 35. All right, so according to the arc length formula that we have, we need the derivative of this function. Well, when we take the derivative of this function, we just get x to the 1/2. And then with the formula, remember we take the derivative and we square it. So when we square the x to the 1/2, we get x. So we just have the square root of 1 plus x in the integrand, and we're going to integrate that from 8 to 35. So this integral expression is going to give us the arc length that we're interested in. Antiderivative of this is going to be 2/3 times 1 plus x to the 3/2. Plug in your endpoints, and I made the numbers so that those come out nicely, and you should get 126.